Kia ora team, welcome to Level 2 Chemistry. We are going to go through the 2023 Structure and Bonding paper. So follow along with me, see how you go. This will take longer than an actual exam because I'll probably do some teaching on the side as well. So question 1, ethanol can be used as a biofuel. Biofuels are formed from materials made by living organisms. The production of ethanol and carbon dioxide from glucose is shown in the following equation below. Is this process endothermic or exothermic? Provide a reason for your answer. Okay, so just to recap, endothermic means energy is going into the reaction. Endothermic. Exothermic, think of exo as exoskeleton, which is on the outside, so energy is being released to the outside surroundings. So the question is this process endothermic or exothermic? Well, we can look at the delta RH value. We see that it's negative, so it's going to be exothermic, which means exothermic, this reaction is exothermic because the delta RH is negative. This means heat from this reaction is released to the surroundings, and that's a nice, easy, achieved point. Next question. Draw a labelled energy diagram for this reaction showing the reactants, products, and change in enthalpy. Okay, so here's something that we need to understand. Because this is an exothermic reaction, this means that the reactants they're going to have a higher amount of energy than the products over here. The reason why is because energy over time is being released to the surroundings, which means that the products are going to have a lower amount of energy than they began with as products. Okay, so if we're drawing this out, let's start off with the reactants. As I said before, the reactants start off with a higher amount of energy. Over time, this energy is being released to the surroundings, so it's being lost, okay? Which means the products have a lower amount of energy than the reactants. But this is not enough. We need to label this diagram. So here's what I'm going to do. Reactants. Let's be specific. This is my reactant. Anything on the left side of the arrow are your reactants. Anything on the right side of your arrow are going to be products. So we've got products, which is cool. So we've done reactants, we've shown the products, and now we need to just label the enthalpy. So the enthalpy is the change in energy, which is over here, and that is negative 72 kilojoules per mole. Cool, so we've labelled everything now. Fantastic. Next question. Calculate the energy change. Calculate the energy change when 161 grams of ethanol is formed. Okay, so whenever we get a mass value like this, your first instinct should be to convert that into moles. So we want to figure out, first of all, how many moles this is and how much energy this amount of ethanol is releasing. Okay, so first of all, convert to moles. We use this equation over here, N equals little m, which is the mass, over big M, which is the molar mass. Substitute everything in. So our mass that we're given is 161. We pop that into here. The molar mass of ethanol is given to us here, and so we pop that into big M. Pop that into our calculator, and we should get 3.5 moles. So 161 grams of ethanol is the same as 3.5 moles. The next step is to chuck this into some ratios. So from the equation, this is how I like to work it out. From the equation, which is this right over here, we see that 2 moles of ethanol gives off negative 72 kilojoules per mole. So 2 moles give off 72 kilojoules per mole of energy. So how much would 3.5 moles of ethanol, which is what we just worked out here, give off? How much energy would that give off? So 2 moles gives off negative 72. 3.5, how much will that give off? Well, here's the beauty of ratios. Okay, what you do to one side, you do to the other. So to get from 2 moles to 3.5 moles, the common multiple is 1.75. The way I worked that out was 3.5 divided by 2, and I was able to work out that that was the common multiplier, which means to get from 2 to 3.5, I have to times by 1.75. So if I times this side by 1.75, I have to times the other side by 1.75. So to get to 72, to whatever the energy released is, I have to times 72 times 1.75, and that should get me 126 kilojoules released. Okay, so if 2 moles of ethanol releases 72 kilojoules per mole, 3.5 moles, which is what we worked out from here, will give off 126 kilojoules. And the reason why it's kilojoules is because we get to cancel out the moles per litre. They just cancel out. And that is worth a merit. Okie dokie. B. The Lewis diagram for ethanol is shown below. Compare, let me highlight so we don't forget, compare and contrast the shape, bond angles around the carbon and oxygen atoms in ethanol. So we want to compare and contrast the bond angles, okay, and the shape around carbon and oxygen atoms in ethanol. Okay, so let's do it. First things first, whenever you are talking about shape, we always have to start off by mentioning the number of negative regions around the central atom. Okay, so what I've written here is, for carbon, well, let's start off with carbon. Carbon has 4 regions of negative charge around it, as you can see here. This is 1, 2, 3, 4. Okay. Next, state the Vesper theory like the question has told us. Okay. The regions of negative charge repel for maximum separation into a tetrahedral geometry with a bond angle of 109.5. Okay, so just to remind you, the Vesper theory is all about the fact that negative regions will want to repel each other. Like repels like, okay? Okay, so the regions of negative charge repel for maximum separation. Because there's 4 regions of negative charge, they will repel into a tetrahedral geometry, okay? They will repel into a tetrahedral geometry. Okay, so the bond angle in a tetrahedral geometry is going to be 109.5, which is talked about here in this table. Next, you're going to state the shape based on bonding and non-bonding regions. It's important to know that shape is different to geometry. So geometry is based on the number of negative regions around an atom, whereas shape is dependent on the number of bonding regions and non-bonding regions. So as you can see here, all of these regions are bonded, okay? There are no lone pairs around the central atom, carbon. So here's what I said. Since the carbon atom has 4 bonding regions and 0 non-bonding regions, the overall shape around each carbon is tetrahedral, same as the geometry, okay? So the geometry and shape will be the same as long as there are no lone pairs of electrons. Fun fact. Okay, using the same template that I provided up here in the grey, you want to use that same template for oxygen, okay, because we're comparing and contrasting. So, as you can see, oxygen, if we're talking about the number of negative regions around the central atom, you can see that there's 1, 2, 3, 4, okay? The Vesper theory states that these regions will repel for maximum separation into a tetrahedral geometry because there's 4 regions of negative charge. Okay, the shape. Now the shape. Because there are 2 bonded regions and 2 non-bonded regions, let's have a look at what I wrote about it. So in comparison, oxygen has 4 regions of negative charge, cool. These regions repel for maximum separation into a tetrahedral geometry with a bond angle of 109.5. Since oxygen has 2 bonding regions and 2 non-bonding regions, the overall shape is bent. So we've compared and contrasted that very nicely. We've done what the question has asked us. We've contrasted the shape, bond angles, and we've referred to Vesper theory. So all of that is done. Cool, that was worth an excellence. Okie dokie, last question before we head into section 2. So take a breather, we are 1/3 of the way through almost. Okay. Ethanol is a major component in alcohol-based hand sanitizers. A student noticed that after rubbing the hand sanitizer on their hands, it readily evaporated, leaving their hands feeling cool. The equation for evaporation of ethanol is shown below. Over here. Okay, so see it's turning from a liquid to a gas. We know that it's evaporating. Okay, during evaporation, okay, I'm giving a little bit of a hint here. During evaporation, can you see that it's going from a liquid to a gas? Which means that bonds have to be broken for it to change state, okay, for evaporation to occur. And for bonds to break, energy has to go in to break these bonds to turn it into a gas and for this hand sanitizer to evaporate. Okay? So, based on what I've just explained, circle the word that best describes the change in enthalpy for the evaporation of ethanol. Well, I gave you the answer. Let's see if you can work it out. Okay, what did you get? Well, the correct answer is that it's a positive delta RH. Anytime it's a positive delta RH, it refers to an endothermic reaction where energy is going into the bonds to break it. Okay? So well done if you got that. Better luck next time if you didn't. Okay. Explain why ethanol readily evaporates and why the evaporation of ethanol results in the student's hands feeling cool. In your answer, let's get our good old highlighter out. Consider the transfer of energy occurring during the evaporation process. Refer to structure and bonding present in ethanol. Okay, I feel like starting off with first explaining the structure and bonding of ethanol. And then we could link it back to the context. So ethanol is made up of non-metal atoms, okay? Non-metals. So, because it's made out of non-metals, we know that it's going to be molecular. How do I know that it's made out of non-metals? Well, anything on the left side of the periodic table from the zigzag are going to mainly be non-metals, okay? So, ethanol is a molecular substance, okay, which contains weak intermolecular forces between the molecules. These forces only need a small amount of heat energy to be broken because they're weak, okay? This is why ethanol readily evaporates. So you've got to always link to the context, okay? We've talked about the structure, we've talked about the forces. Always refer to the forces which allow for the structure to be the structure that it is. And then talk about the weakness or the strength of these forces and how much energy is needed to break them. So structure and bonding, done. Next, we need to look at the transfer of energy occurring during the evaporation process and eventually link it to why the students' hands feel cold. So, here's what I wrote. As the student rubs their hands with hand sanitizer, what's happening? Well, essentially there's friction being created, which causes the production of heat energy. So that heat energy caused from all that rubbing is transferred from the student's hands to the ethanol, okay, which is in this hand sanitizer. So that hand sanitizer or ethanol absorbs that heat energy, which is endothermic, okay? The absorption of that heat from the hands, rubbing of the hands, is an endothermic reaction. So once this heat is absorbed into the ethanol, it goes into breaking the weak intermolecular bonds which holds ethanol together, and that leads to the evaporation of ethanol from its liquid state to a gaseous state. This process draws heat from the student's hands, and because it's drawing heat out of the student's hands, this gives the sensation of feeling cool. And that is how we do it. Alright, we made it to question 2. Take a moment to have a little break before we unravel this bad boy. Alright, back to the grind. Question 2, let's smash it out the way. So ethanol is used as a fuel by reacting it with oxygen gas in a process called combustion. The combustion of gaseous ethanol is shown below. So here's the reaction. This is how much energy is released. Whenever we're given a table like this, we know it's going to be that kind of question where it's energy of bonds broken minus energy of bonds formed. Easy peasy. So the first thing we need to do is we need to work out the energy of the bonds broken. So the aim of the game eventually is to figure out how much energy is released just by the single, by this O bond over here, okay, this double O bond. So let's follow the equation, energy of bonds broken. So let's start off with our first molecule of the bonds being broken, which is over here, drawn out for us nicely. We have to figure out how much each bond is worth and add up that energy. So as we can see here, we've got 1, 2, 3, 4, 5 CH bonds. One CH bond is 413 kilojoules per mole. But because there's 5 of them, we have to times that value by 5, and that gives me 2065 kilojoules per mole. We've also got a CC bond. There's only one of them, so that's going to be 348 kilojoules per mole. Then we've also got one CO bond, which is worth 358. And then one OH bond over here, which is worth 413 kilojoules per mole. So we've done this molecule here of the bonds being broken, and just a heads up, anything that's usually on the left side of the arrow are bonds that are going to be broken, whereas anything on the right side of the arrow are bonds formed. Okay, so we've got this to deal with. We've got to figure out the energy within those bonds. So there's 3 lots of O2, okay. What I like to do is I always like to draw things out. So I've got 3 lots of O2. I have to figure out what one of these bonds is worth in terms of energy. Okay, because that's not given to us, that's what we're going to have to work out eventually. So all I can do right now is say that I've got 3 lots of O double bonded O's, which is equivalent to just 3x if I'm becoming algebraic fancy. So here's the equation for total bonds broken. Adding all of these up gives me 3,234 plus the 3x from our oxygen. Okay, now let's work out the total bonds formed. Okay, let's start off with CO2. Let's work out the bonds formed, energy of the bonds formed in this. So as we can see in the reaction, there's 2 lots of it. So I'm going to go ahead and draw 2 lots of CO2. As you can see, now we have 1, 2, 3, 4 lots of this CO bond. So we're going to have to times 805 by 4. And we get this value here. Let's not forget that H2O, okay, we have to work out the energy that is formed here within these bonds. And as we can see that there's three lots of them. So let's draw it out. Always handy to draw them out. As you can see, there are 1, 2, 3, 4, 5, 6 OH bonds, okay? So 1 OH bond is worth 463. So 6 OH bonds is worth 2,778. Adding those together, okay, adding these values of CO2 and H2O together, the total energy of the bonds within those molecules will get 5,998 kilojoules per mole. So when we've got this equation now that we can use, okay, and we could substitute the things that we have. So the delta RH is already given to us over here, and so we could substitute that in the equation. Bonds broken is 3234 plus 3x, and then minus the bonds formed, which is 5998. Okay, so what I can do is a little bit of algebra and rearranging to find what this X is, which essentially is this O double bond. Okay, so with a bit of rearranging, what I've done is I have condensed the like terms. So I've added 3234 with minus 5998 to get me negative 2764. And to isolate or get rid of this, so I'm left with just 3x on this side, I plus 2764 to cancel it out. And what I do to this side, I have to do to the other. Okay, so now I've got this equation here. Then I'm going to condense the like terms on this side. So if I plug this into my calculator, I will get 1394. And so now I have to get rid of this 3, so I can just have x on one side. So I divide, because it's currently being times by 3, I divide this side by 3 and cancel those out. That means I have to divide this side by 3. Okay, and so now I'm left with x, which equals 465 kilojoules per mole, which is the average bond enthalpy of the OO bond. Done! How easy was that? You got to be careful. Make sure you don't forget any bonds, okay? And you draw things out because that really helps. Don't forget units as well. Okay. The product of combustion of ethanol are carbon dioxide and water. This is carbon dioxide, this is water. Carbon dioxide contains carbon and oxygen atoms. Oxygen is more electronegative than carbon. Draw 2 arrows or add dipole symbols onto the carbon dioxide molecule shown below to represent the bond dipoles present in carbon dioxide molecule. Okay, so I'm going to work with dipoles, which are the fancy little symbols. And so it tells us that oxygen is more electronegative. So it's going to be assigned a negative dipole. The reason why it's a negative dipole is because electronegativity is all about an atom's tendency to pull electrons to itself, attract electrons to itself. So because oxygen is more electronegative, it means that it has a stronger pull on electrons. Electrons are negatively charged, so that's what makes oxygen slightly more negative and carbon slightly more positive. Okay. So if we were to add dipoles, these arrows just for the sake of it, these dipoles would essentially go in opposite directions, okay, and cancel out. So, keeping that in mind, circle the word that describes the polarity of each molecule below. So these dipoles, okay, are going to cancel out in carbon dioxide for a few reasons. First of all, okay, the carbon dioxide molecule is linear. It has the same atoms around the central atom, and there are no lone pairs of electrons around carbon, which means that it is going to be symmetrical. So because of the symmetry and the other factors that I've mentioned, the dipoles are going to cancel out, okay, and that results in carbon dioxide being, drum roll please, non-polar. H2O, on the other hand, okay, yes, it has the same atoms around the oxygen, which is the central atom, and yes, it's bent with Floor regions, and yes, it has lone pairs. Because of the lone pairs, this means that H2O is not symmetrical, which means that the bond dipoles are actually not going to cancel out. So because the bond dipoles don't cancel out due to the lack of symmetry, water is actually polar. So I've kind of explained to you the gist of it. What we have to do now is put it into words. We have to compare and contrast it. So compare and contrast the factors that influence polarity of these two molecules. I've done CO2 for you, but I haven't done water. So I'm hoping that my template for CO2 will prompt you to do a similar explanation for water. It's pretty straightforward, but I want to challenge you to be able to do that on your own. Okay? I have verbally explained it, but it'll be up to you to write it out. Okay, so CO2. Whenever we're talking about explaining polarity questions, this is the structure that I like to use. Okay, so first of all, let's talk about the polar bonds of CO2. CO2 has polar bonds between carbon and oxygen, with oxygen being the most electronegative. Now we have to talk about electronegativity. This means electrons spend more time around oxygen than carbon, which results in a bond dipole. And I've shown the bond dipole here. It's a good idea to do that. Then I want to talk about the symmetry. So symmetry takes into account these three things. CO2 has a linear shape with the same atoms around the carbon atom. Okay. There are no lone pairs of electrons around the central atom. This results in the bond dipoles being arranged symmetrically. Okay. Due to the symmetry, there is a molecular dipole present as the dipoles cancel out. My bad. This is meant to say there is no molecular dipole present. Whoopsies. Having a bit of trouble adjusting that. There is no molecular dipole present. You'll just have to make that adjustment yourself. There's no molecular dipole present. Okay, so because there's no molecular dipole, the dipoles actually cancel out, as I've shown you before. Therefore, CO2 is non-polar. Okay, so these are the things you'd kind of have to mention for any polarity question. Use this template. Strongly recommend. Okay, next question. The combustion of fuels can result in toxic byproducts such as carbon monoxide. A catalytic converter can be used to convert these compounds to less harmful substances. Catalytic converters often contain the element palladium, Pd. Complete the table below for each of these substances in their solid states. Carbon monoxide. Okay, carbon and oxygen. What type of solid is this? It's molecular because it's made out of non-metal atoms. Type of particles, it's made out of molecules. I want you to understand that the attractive forces, which is intermolecular forces that are weak, occur between the molecules, okay? So, molecular solids are made out of molecules which have intermolecular forces. But within these molecules are made of atoms which are covalent. But we're focusing on the molecules and the forces between those molecules, which is why it's intermolecular. Okay? So it's important when you're explaining this later on that you're talking about the intermolecular forces that occur between molecules, not atoms. Okay? I want to make that really clear. Okay. Anyways, Pd, palladium, is a metallic solid. Type of particles, it's made up of metal atoms or metal cations and delocalized electrons if you want to add that bit of detail. Better to go overboard than underboard. Attractive forces are metallic bonds, which are quite strong. Okay, make sure to revise these things, guys, if you have forgotten. So the question is, when exposed to exhaust gases greater than 300 degrees Celsius, palladium remains in its solid state. So even at 300 degrees Celsius, this metal remains solid. It doesn't change state. Use your knowledge of structure and bonding to explain the high melting point of palladium. So when we're talking about structure and bonding, we have to talk about what makes up palladium. We have to talk about the bonding between the type of particles, okay, and how strong they are. So this is what I've written. Palladium is a metallic solid made up of metal cations, which are held in a lattice and surrounded by a sea of delocalized valence electrons. Positive metal nuclei are attracted to surrounding free-flowing valence electrons, which results in strong non-directional metallic bonding. Okay, I'm a bit of a visual learner, so let me help you out for those of you who are also visual learners. So if we're looking at a metal, okay, it is held in a lattice, okay. I'm going to do 3 sheets here. And these are positive, these are the positive nuclei, okay. And so around the positive nuclei are free-flowing electrons, and they are basically like a sea, okay. They're a sea of delocalized valence electrons, and they're just floating around the positive nuclei. So, since they're moving around, the attraction between these electrons and the positive nuclei are going to be in all sorts of directions. So this is why it's a non-directional forces which are occurring here, okay, because they're free-flowing, the direction of forces is always changing, okay. And so this explains the structure and the bonding. These non-directional forces are strong. This is a key thing to know. So because of the strong non-directional metallic bonding, we need to link it to the context now and explain why such a high melting point is needed to melt palladium. So due to these strong forces of attraction, a lot of heat energy is required to overcome the strong metallic bonds. This explains why palladium has a high melting point and doesn't melt even at 300 degrees Celsius. That's worth a merit. Okay, Lewis diagram time. Let's do it. We're up to question 3, the final leg of the race. Let's do it. Okay, so for this question, you're going to need to use your resource sheet don't mind me while I get mine up. So, what you also have to remember is that there are a few exceptions when drawing Lewis diagrams. And Lewis diagrams are cool because they help us visualize molecules that we actually cannot see with our naked eye. So pH3, let's start off with drawing the Lewis diagram for this molecule over here. The first thing I do when I deal with Lewis diagrams is I like to draw a table. So let's draw a table. I'm going to squeeze one right over here. P, there's 3 H's. So now that I've established what atoms are in my molecule, I want to see how many valence electrons are in around these atoms. So how do I do that? Well, I look at the periodic table in front of me, and so phosphorus, P, is in group 15. What's the second digit of 15? 5. So phosphorus has 5 valence electrons, 5 outer shell electrons. Hydrogen is in group 1, so that means it has 1 valence electron. Right, now, based on this, I'm going to start another column. This column is going to be to do with what this atom needs to have a full outer shell. So according to the octet rule, you need 8 electrons in the outer shell to be fully stable. Okay. Currently, phosphorus has 5, so how much more does it need? Well, it needs 3 to make a full octet. Hydrogen is an exception to this rule. It only needs 2. Currently it has 1, so we need 1 more to have a full outer shell of 2. The needs, okay, is also an indicator of how many bonds these atoms will form, and that's going to be very clear as soon as I start to draw these out. Okay, so I have to pop the neediest atom in the middle. That's my next step. As you can see, phosphorus needs 3, whereas hydrogens only need 1 more. So phosphorus is going in the middle, and the hydrogens are going to be around. So according to this column over here, phosphorus needs 3 extra electrons to have a full outer shell, and also just 3 bonds. Okay, so I'm going to draw that. The only things it could bond with is the hydrogens. Okay, so now that's all fine and dandy. The next thing I need to do is I need to make sure that every atom is happy. So I have to check if phosphorus has 8 electrons around it. I want you to know that one of these bonds is worth 2 electrons. So currently it has 1, 2, 3, 4, 5, 6, 7, 8. Now it's happy. I've added some lone pairs of electrons. So now it satisfies the octet rule. Let's check out the hydrogens. Are they happy? Do they have 2 in their outer shell now? Well, because of this bond, they're able to share electrons with the phosphorus. So let's count. 1, 2. Yep. 1, 2, and 1, 2. So everyone is happy, which is great. Let's move on to the next atom. So we've got BCl3. Again, let me draw my lovely table. BCl. There are 3 lots of Cl's, which is fantastic. And then let's look at the valence electrons. Okay, B, also known as boron, is in the 13th column of the periodic table. So there's 3 valence electrons. Chlorine is in, I believe, group 17. And so that means there are 7 valence electrons. How many more does boron need to have a full outer shell? You might be thinking 5, but here is where you have tripped up, my friend. Boron is another exception, so you have to be familiar with the exceptions. Boron only needs 6 electrons in its outer shell to be fully stable. So it currently has 3, it needs 3 more. Chlorine has 7. It is not an exception, it follows the normal octet rule, so it needs 1 more. Okay, almost there. What is the neediest atom? The neediest atom seems to be boron because it needs 3, whereas chlorines need only 1 more to have a full outer shell. So chlorines can go around. So according to this column over here, yes, boron needs 3 extra electrons, but it also means that it forms 3 bonds. So I'm going to go ahead and draw those 3 bonds around boron. Chlorine only needs 1 bond, which has been satisfied, but the last thing I need to do is I need to see if these atoms are happy and if they have enough electrons around them. So boron only needs 6. So let's count if it has 6. 1, 2, 3, 4, 5, 6. Beautiful. Chlorine needs 8. Currently it has 1, 2. So I have to add more lone pairs of electrons to make it happy. So it's got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Wonderful. As you can see here, I've kind of revealed the answers for the shapes. There's a free little answer for you. Make sure you study them up anywho. But let's finish these Lewis diagrams and we could talk a little bit more about these shapes. Okay, so last one to go. Let's draw our beautiful table again. So we've got carbon, oxygen, and Br. I've got 2 of those. Okay, let's find out the valence electrons for each of them. So carbon is in group 14, which means that it has 4 valence electrons. Oxygen is in group 16, so it has 6 valence electrons. Br is in group 17, so it has 7 valence electrons. How many more does it need to have a full outer shell? Don't worry, this time there are no exceptions within these atoms. Okay, so we've got carbon, it's got 4 currently. It needs 4 more to have a full octet. Oxygen has 6, it needs 2 more to have a full octet. Br has 7, and it needs 1 more to have a full octet. Which one's the neediest atom? It is carbon because it needs 4 electrons to have a full outer shell, whereas everything else needs less. So let's pop that in the middle and let's pop everything else around the outside. Okay, so as you can see here, this is going to be a little bit of a trip up for some, but don't worry, I got you. Carbon, it says that there are 4 bonds needing to be formed. Okay, but there are only 3 atoms, so what do we do here? Well, this tells us that there needs to be a double bond between one of these atoms. Which one is it going to be? Well, is it going to be between the carbon and Br? Well, I don't think so, because as you can see in our table, Br will only form 1 bond. Both of these Br atoms will form 1 bond. So it can't be the Br atoms according to the table that we've made. Okay, so it cancels these guys out. So the only thing left is the oxygen. So there has to be a double bond between the oxygen, and that checks out because, as you can see in our table, oxygen needs to form 2 bonds. Okay, so carbon currently has 4 bonds, which is the maximum amount of bonds for carbon. Oxygen has 2 bonds formed. Cool, that's happy. And the BRs have 1 bond each, which is great. It all checks out. Another thing that we need to be mindful of is, are all of the atoms happy? Do they all have enough electrons to meet the octet rule? Well, carbon, let's have a look. It's got 1, 2, 3, 4, 5, 6, 7, 8. Oxygen, does that have enough? It's got 1, 2, 3, 4. No, it doesn't have enough. 5, 6, 7, 8. Do the Br atoms have enough? It's got 1, 2, 3, 4, 5, 6, 7, 8. And then 1, 2, 3, 4, 5, 6, 7, 8. Now it's happy. Everyone's happy. This is what we like to see. As for the shapes, again, that's a free pass for you. But basically, remember, shapes are dependent on the number of bonding regions and non-bonding regions. You cannot assume it's the same as the geometry. So because there are 4, for example, 4 regions of negative charge around the central atom, the geometry is going to be tetrahedral, okay? But because there are 3 bonded and 1 lone pair, the shape is going to be a trigonal pyramid. Over here, there are 3 regions of negative charge around the central atom. There are no lone pairs, so the geometry will be the same as the shape. It's going to be trigonal planar. Same for our last molecule over here. Okay, almost there. Hang in there, team. Okay, so the formation of carbonic dibromide is shown in the equation below. Calculate the mass of carbonic dibromide formed when 1,150 kilojoules of energy is released. I've given you a top tip here. Whenever you get 2 energy values, you can divide one by the other to find out how many moles is in our molecule of concern. So we've got 1 energy value here, which is shown in the equation. And then we've got the energy released when a mystery mass of carbonic dibromide is present, okay? So we want to figure out, instead of working out the energy released from mass, like we did in the other question, in this question, it's flipped it around. We want to figure out the mass when this much of energy is released. Okay, so again, let's translate things to moles over here. That's our first step. So as I said before, we've got 2 energy values. If we divide one by the other, we are going to get the number of moles in carbonic dibromide. So how do I know what's being divided by what? Well, it is going to be the wanted energy. Okay, I'm going to call this the wanted energy, the one that's in the question, divided by the energy that is in the actual equation, okay? So wanted energy divided by energy in the equation is going to give me 15.86 moles. But just bear in mind that this energy value, 145, is for 2 moles of the carbonic dibromide. So I actually had to divide it by 2 to find out the energy given off by one of these, not 2, which is what I've done here in the equation, and that has given me 15.86 moles. Okay, so just be careful with that. Now that I have the moles of carbonic dibromide, I can use N equals little m, which is mass, over big M, which is molar mass, and rearrange it to find out what the mass of carbonic dibromide is. So plug everything in, and then I have got 2,980 grams of carbonic dibromide, okay, forms this much of energy. So we've kind of had to work backwards, but this is what you do for a question like this. Okay, moving on to the next question. Now that we've figured out that the mass associated with this energy release over here is in fact 2,980 grams, the next question is asking us, a chemist wishes to store this mass of carbonic dibromide in a 1 litre flask. If 1 ml of carbonic acid has a mass of 2.58 grams, will they be able to contain it within the flask? Will they be able to contain this many grams in a 1 litre flask? So this is when we use ratios again. So we know that 2.52 grams is equivalent to 1 ml. How many mils is 2,980 grams equivalent to, and is that going to fit in a 1 litre flask? Okay, so again, ratios, let's do it. How do I get from 2.52 to 2,980? Well, I divide 2,980 with 2.52, and I should get 1182. Okay, so what I do to this side of the ratio, I have to do to the other side. So 1 ml times 1182 will give me 1182 mils. So 2.52 grams is equivalent to 1 ml, and based on my ratio, 2.980 is equivalent to 1,182 mils. So can this, the question, let's go back to the question, can 2,980 grams fit into 1 litre? Well, 1 litre is 1,000 mils. So this is bigger than 1,000 mils. Therefore, this mass of carbonic dibromide cannot fit in a 1 litre flask. Cannot fit in a 1 litre flask. I will leave you to write the answer for that. It's basically what I just said. 2,980 grams of carbonic dibromide will not fit in a 1 litre flask, as it's equivalent to 1,182 mils. Don't forget units. Well done, team, almost there. Okay, C. Carbonic dibromide does not conduct electricity in either the solid or liquid state. However, another bromine-containing compound, lithium bromide, conducts electricity when molten, but not when solid. Elaborate on the electrical conductivity of both carbonic dibromide and lithium bromide, with reference to structure and bonding in each compound. Okay, let's start off with structure and bonding of carbonic dibromide. So as you can see here, I've written carbonic dibromide is a molecular solid consisting of molecules held together by weak intermolecular forces. See how I've said that the weak intermolecular forces is occurring between molecules, not atoms. Okay, so be mindful of that. Atoms are bonded by covalent bonds. Alright, now we have to link this to conductivity like it states in the question. Since there are no free-flowing charges, okay, this means that carbonic dibromide is not able to conduct electricity in any state, okay? So we've done a good job of linking that back to the context. Now we want to compare and contrast this to lithium bromide. So let's go ahead and do that. Let's talk about the structure and bonding first. In comparison, lithium bromide is an ionic solid consisting of alternating lithium cations and bromine anions. Okay. Lithium cations means that these are the positive ions. Anions are negative, okay? These are held together by strong ionic bonds, which form a 3D lattice structure, okay? So these strong ionic bonds are able to occur between these cations and anions because of the electrostatic forces between them. Opposite charges love to attract, and so that's why these ionic bonds are very strong and hold the lithium bromide in a 3D lattice structure. Okay, now we have to link it back to the context. In a solid state, lithium cations and bromine anions are fixed in the lattice structure, and there are no free-flowing charges, okay? There are no free-flowing charges in a solid state for lithium bromide. In the state, lithium bromide does not conduct electricity. However, in a molten state, the ionic bonds are broken, which allows the lithium ions and the bromine ions to move and pass electrical current because they become free-flowing. So, this is a good comparison between carbonic dibromide and lithium bromide as well. D. By referring to the attractive forces between particles, explain why lithium bromide is unable to dissolve in non-polar solvents such as cyclohexane. That's kind of them to tell them that cyclohexane is non-polar, but can dissolve in polar solvents such as water. Okay, so why can't lithium bromide not dissolve in non-polar, but can dissolve in something that is polar? Well, remember, like dissolves in like. So, if lithium bromide is polar, it's not going to dissolve in something that is non-polar. Okay? It has to dissolve in something that is polar, such as water. Okay, so the first thing you want to state is the solubility rule, which is kind of what I just explained. So, for lithium bromide, which is the solute, for it to dissolve, the attractive forces between the solvent, which is the water, and the solute, which is the lithium bromide, the attraction between these two things need to be stronger. They need to have stronger attractive forces to overcome the forces holding lithium bromide, okay? So the forces between H2O and lithium bromide have to be stronger than the forces inside of lithium bromide, okay? This needs to be broken apart, and that's only possible if the forces of attraction between these two things are strong enough. Okay, so this is possible when the solvent is polar, such as water. So the negative dipoles of water attract to the positive lithium cations, and then the positive dipoles of water, okay, which are the hydrogens, attract to the bromine anions. How do I know that the oxygen is the negative dipole and the hydrogen is the positive? Well, always remember Fonkel. So fluorine, oxygen, nitrogen, and chlorine, these are the most electronegative and in that order as well. So oxygen is within this mix, which means that it is quite electronegative in comparison to hydrogen. Anyways, the electrostatic forces of attraction are sufficient to overcome the ionic bonds present in lithium bromide, okay, allowing it to dissolve in polar solvents such as H2O. Okay, so that's an explanation of how the solubility occurs. I've drawn a diagram just because it's easy to understand. So as you can see, lithium bromide is held together by positive lithium cations and bromine anions. And so between these are strong ionic bonds, which are held together by electrostatic forces of attraction. So the forces between the water, polar water, have to be strong enough to overcome these ionic bonds within lithium bromide. Okay? And so what happens is the positive ends of water attract to the negative parts of this lattice, and then the negative ends of water attract to the positive parts of the lattice and pull it apart to make it this right over here, okay, to dissolve it. And now it can actually conduct electricity because there are free-flowing charges. Alright, now we need to compare it to the solubility in cyclohexane. So in contrast, lithium bromide cannot dissolve in non-polar solvents such as cyclohexane. Why? Well, cyclohexane does not have dipoles, which can form attractions with the lithium and the bromine. Okay. Since the forces of attraction between cyclohexane and lithium bromide are not sufficient to overcome the attractive forces within lithium Li plus and Br minus, the ionic lattice remains intact and lithium bromide does not dissolve in cyclohexane. Okay, so this is a great compare and contrast example, but this essentially is solubility in this context. Okay. Please let me know if you have any questions. Please highlight any points that you need to revise yourself, but keep chipping away. Hope you smash the exams. Stay tuned for more past exam help. Thanks, team.